Okay, you should remember this equation. Again, I'm repeating. There are two things we have learned. One is inductance of a conductor due to internal flux. Now external flux. Both equation you just remember. Due to internal flux, inductance is constant. That is what we have observed. So L is equal to 0.5 multiplied by 10 to the power of minus 7 Henry per meter. That is what we have learned. So due to external flux, L is equal to 2 into 10 to the power of minus 7 ln d2 divided by d1. These two things you should remember. Okay. So this is a fundamental. Now what we have learned is that we have considered one single conductor, and for that conductor, inductance property will be will exhibit, and that can be due to internal flux as well as external flux. So that we have estimated. Now let me move on to the next small thing. What I'm going to do is that I'm going to consider a single phase transmission line. Okay, I'm going to consider a single phase transmission line. So for that single phase transmission line, how to evaluate this L, that we are going to learn. Okay, so take down inductance of a single phase 2-wire line. So in single phase, how many conductors will be there? In single phase. In single phase, how many conductors will be there? 2. So one is for single phase AC, one is for phase, another one is for neutral. That's it. Very simple. So this single phase transmission line will have a 2 conductor. One is meant for phase and another one is meant for neutral. So here so in the earlier case, whatever we have learned, we have considered one single conductor. Here 2 conductors are going to come. That is the difference. Okay, we are going to learn very simply. So single phase line, it will have conductor number 1. And for that, let me assume that the radius of the conductor is R1. Right? So one more conductor I am considering. And for that conductor, the radius is assumed to be R2. Right? So let me assume that single phase transmission line, these 2 conductors are placed at a distance D. Placed at a distance D. Right? So now we have 2 conductors. Am I correct? So conductor number 1 and conductor number 2. So let me assume that the inductance of a conductor 1 is L1. So the inductance of conductor 2 is L2. Right? So now coming to conductor 1. So conductor 1, L1 inductance. This inductance can be due to internal magnetic flux, as well as external magnetic flux. Similarly, for conductor 2, L2, this can be due to internal magnetic flux, as well as external magnetic flux. Both, if you are adding it, you will get the inductance value. Right? So this is what about the individual conductors. That is, L1 represents the inductance of conductor 1, L2 represents the inductance of conductor 2. If you add L1 and L2, the inductance of a single phase transmission line can be estimated. Okay, if you add L1 and L2, you can get the inductance of a single phase transmission line. Okay, now let me move on to the derivation. First, you may take down, assume that inductance of conductor 1 is L1. So now L1 is the inductance of conductor 1. So this L1 comprises of the inductance due to external magnetic flux as well as internal magnetic flux. That if you are adding, you will get inductance L1. You may take down. Now inductance of conductor 1, L1 is equal to the summation of inductance due to internal flux of conductor 1 and inductance due to external flux of conductor 1. Now, can anybody say L1 int? So you can look at this in that. So it is mentioned that L1 int is the inductance of conductor L1 due to internal magnetic flux. So L1 internal is equal to just think about the previous derivation and tell me what is the answer. L1 int. Yes. So L1 internal, so that is the inductance due to internal magnetic field is equal to 0.5 into 10 to the power of minus 7. Don't forget about this. That is the reason why in the beginning we have landed. So you may take down inductance due to internal flux of conductor 1 is given by L1 internal 0.5 into 10 to the power of minus 7 Henry per meter. This is from the previous derivation. Similarly, so inductance of conductor 1, that is L1 due to external flux. So external flux between 2 points. So here the point of, you can look at this, the fluxes between the two conductors, that is separated by a distance d. Hence the inductance due to external flux of conductor L1, that is L1 external, can be written as 2 into 10 to the power of minus 7 ln d divided by R1. So this is an important thing. So this is right? So now equation number 2 represents the inductance of conductor L1, that is L1, due to external magnetic flux that we have evaluated, that is internal as well as the external magnetic flux impact in the inductance is evaluated. Now it is time to evaluate the inductance of conductor 1, that is L1. So L1 is the summation of L1 internal plus L1 external. So both, if you are adding, you will get an expression like this. This is L1 internal. This is L1 external. Right? Now we are going to add these two things. Okay. So for simplifying this, so just for a simplification, mathematical simplification purpose, so there are two terms present in this equation number 3. What I'm going to do is that I'm going to take a term 2 into 10 to the power of minus 7 as a common term. Okay. Just to take 2 into 10 to the power of minus 7 from these two terms. 2 into 10 to the power of minus 7 for simplification purpose. Okay. No other, the logic is to get a simplified expression. That's it. So take 2 into 10 to the power of minus 7 as a common term. So if you are taking 2 into 10 to the power of minus 7 as a common term, you will get a resultant like this. Just to verify your answer. So now, here again for mathematical simplicity, so 0.25 can be written as 1 by 4. It is well known. Am I correct? So 1 by 4, can I write like this? Ln E to the power of 1 by 4. Can I write like this? Ln E to the power of, can I write like this? So this is equal to 0.25. Okay, this is for mathematical simplicity. 0.25, just I am writing it as an ln e power of 1 by 4. That's it. You may take down. So 0.25, it is known that 0.25 is equal to 0.25 is equal to ln So you may take down. It is known that 0.25 can be written as ln e power 1 by 4. So ln e is 1. That's it. So ln e is 1. So that I am writing it as ln e power 1 divided by 4. So this equation number 5, I am going to substitute in equation number 4. Equation number 4, if you are doing it, so instead of 0.25, you can have a look at this. So what I have written is that ln e power of 1 divided by 4. Now, equation number 6, look at equation number 6. It seems to be ln A plus ln B. So ln A plus ln B can be written as ln A plus ln B can be written as ln AB. That's it. So do that mathematical simplification and write the answer. So ln A plus ln B can be written as ln AB. So that is what you have to do is that you have to multiply e power 1 by 4 with d divided by r1. That's it. Right? So now, if you do ln AB, you will get an answer like this. So e power 1 by 4, I have, for simplification purpose, I have brought it down. E power minus 1 by 4, I have written. That's it. Just a multiplication of these two terms, first term and this term. If you are multiplying, you will get an answer like this. For simplicity, I have brought e power 1 by 4 to the denominator. That is the reason why it is written as e power minus 1 by 4. Right? So now e power minus 1 by 4, just put it in the calculator and say me what is the answer. E power minus 1 by 4. E power minus 1 by 4. It is equal to
0.7788.
7788. That's it. Okay. So now what I'm going to do is that this equation number 7, I'm going to write like this. Here, this R1 e power minus 1 by 4, I'm going to consider it as R1 dash. This R1 dash is equal to 0.7788 R1. That's it. right? So now this expression 8 is meant for inductance calculation of conductor 1. So that you can estimate with this expression. Similarly, there are two number of conductors. Am I correct? We have evaluated conductor 1 inductance only. So there is again one more conductor, that is conductor 2. In the similar fashion, if you are doing the derivation, again you will get the expression. Can anybody say what is the expression for inductance of conductor 2?
Sir, it is same, sir. R1 dash becomes R2 dash.
Yes. So L2 is equal to 2 into 10 to the power of minus 7 ln D divided by R2 dash. So here R2 dash is equal to R2 multiplied by 0.7788. 0.7788. So now it is time to evaluate the total inductance. So now we have estimated individually the inductance of conductor 1 and inductance of conductor 2. That is what we have done it. So now it is time to estimate the total inductance of a single phase transmission line. That is going to be the summation of L1 and L2. Single phase 2 wire line. L can be written as L1 plus L2. Substitute L1 and L2, simplify it. Substitute L1 and L2 in this expression and find L. So L is equal to, just to verify this equation. So if you are substituting L1 and L2 in equation number 10, you will get an expression like this: 4 into 10 to the power of minus 7 ln D divided by square root of R1 dash R2 dash. Okay, just verify it.
Yes, sir.
Yes. Right. Now, so inductance we have estimated. Generally, we have considered two different conductors. Am I correct? Conductor number 1 and conductor number 2. Generally, these conductors will be similar. Same conductors we generally go ahead. That means that R1 will be equal to R2. R1 will be equal to R2. If R1 equal to R2, tell me what is the value of inductance. Substitute R1 equal to R2 is equal to R in equation number 11 and tell me what is the inductance expression. L and D by R. So now what we have learned is, first we have started with one simple conductor. Then now we came to a small single phase transmission line. Single phase transmission line. It is a very simple structure. Am I correct? Simple structure. Now gradually we are going to move on to what could be the AC transmission systems generally. AC transmission system will be of three phase in nature. Am I correct? three-phase in nature. So gradually we are going to move on to the three-phase circuit. So for that reason, firstly, we are going to learn about flux linkage of one conductor in a group. So that fundamental we are going to learn, and from that we are going to move on to deriving the expression for three-phase conductors. Okay, so that we are going to learn it in the next class. So thank you very much for listening to this class. If you have any more clarifications, you can ask me. So thank you very much, and probably